we'll be treating waves and sound. I think this is one of the topics that people barely pay attention to during teachings most of the times. Probably optics might be more of attention, but I think sound most of the times people just, I don't know, for different reasons, maybe because of its position in the whole curriculum, but people most of the times they don't seem to get it. So this lesson will be more of like an explain and try to teach the basic concepts and prepare you guys for. So this is week 11, and I again myself. So as I said, we are treating waves and sound, and in this topic we'll be touching wave characteristics and properties. We'll be touching on superposition, sound properties, Doppler effects, and also waves in pipes and strings. So let's see what we have. First off, waves are disturbance that transfers energy from one place to another without a transfer of matter. So this is like, this last portion is like the key to distinguishing waves and probably some other stuffs. It is a disturbance, that transfers energy. So it transfers energy. But now it doesn't just transfer energy, but it transfers energy without transfer of matter. That you would not see the particles going as the thing is probably making the noise. As in this sense that if you are trying to clap your hand to make noise or to create some kind of wave, your hand will not scatter as you're clapping. I'm using sound wave in that sense. Bulb, if you're turning on the bulb for it to display them to show light wave, to reveal light wave, the bulb will not explode, except for some reasons when maybe that the strength of the glass itself has been exceeded and the glass will burst. But normally, the glass will just remain as it is. They will not displace the wire that is used to make the lights come on. They will not get destroyed. The particles will not get scattered. It's just the wave that would be propagated through. So now, they can be classified into mechanical and electromagnetic. So when you hear waves, we have both light wave, sound wave, and magnetic wave, different kinds of wave, but basically they are grouped into just two types of wave. We have the mechanical wave and the electromagnetic wave. So these mechanical waves are those ones that require a medium or a material for them to move, or in other words, for them to be propagated. So mechanical waves, they are waves that require a medium to be propagated. While electromagnetic wave are those kind of waves that they don't necessarily need a medium. And what I mean by a medium is they need something that's either gas, liquid, or solid. They need one of these three phases of matter. That's what they mean by they need a medium. So they need solids to be propagated, or they might need liquids to be propagated, or they may need gases to be propagated or to get propagated through. So for electromagnetic wave, they don't have any medium, meaning that in a vacuum, I hope you guys know what a vacuum is. A vacuum is a place that is void of every form of matter. Like it's a pure space that there is no air. There is no air at all. So we don't have any, it's a space. So meaning that there is no solid inside. Like meaning that there is not composed of solid. It's not composed of liquid. It's just composed of an empty surrounding. An empty surrounding where there is no single matter present except the one that are being dropped into it. So these there's no dominant matter, if I would say it that way, present in it. So these are the kinds of electromagnetic wave, the kind of wave that can get propagated medium or in the absence of a medium. That's example in a vacuum. So examples of sound, examples of these waves include sound wave, water wave, light wave, and so on. So they include water wave, sound wave, and so many other waves. So let's see what we have in our next slide. So we have wave characteristics. So now, as we've known that waves are a particular kind of entity.
Your
the
voice is
high.
not like clear. It's cracking.
Oh, I don't know. Can you hear me clearly now? Can you hear
Yes,
me
I
clearly
can.
now? Okay, okay. I don't know. But wave characteristics, we have basically these major wave characteristics. We have the amplitude, we have frequency, we have period, we have wavelength, and we have speed. So I'll start explaining each of them one after the other. So for wavelength, by definition, it can be said to be the distance between two consecutive crests or troughs of a wave. So if you can remember, if you know what waves look like, they look like continuous undulating movements. Sometimes moves like in a snake-like movement. It goes up, come down, goes up, come down. These are how waves move. They move in undulating pattern. So when you now talk about wavelength, you're talking about from one high to another high. The distance between the both of them is called the wavelength. Or if you are going like this from one low to another low, the distance between these two lows are called is called wavelength. So that is what it is. So wavelength is actually the distance between these two highs or two lows. So they also call them crests or troughs. So wavelength is the distance between two highs or different distance between two lows. So amplitude on the other hand is the maximum displacement from equilibrium position. So no, it's not, you don't just need to take only the word maximum displacement. You need to mention that it is from equilibrium position. Because if you don't mention this, you're not actually talking about the amplitude, because when you have these waves moving in their snake-like pattern like this, their center is that center that they call the equilibrium position. So their center is their equilibrium position. So the distance between this center and the top, the highest height, or the distance between the center and the lowest low is what they call the amplitude. The amplitude, it is when you draw the wave, this is the wave going like this. Then you go from the center of the wave. That center is called the equilibrium position. So now from the center line to the highest height that the wave went to, that distance is called the amplitude. And also from the lowest low between these equilibrium points, the lowest low that the wave went to, between the equilibrium point and that lowest low is what they call the amplitude also. So it is that maximum displacement, either upwards or downwards, that a wave seems to propagate. So another characteristics of wave that we'll be talking about is the frequency. So frequency, this is the number of oscillations or number of waves that passes a point in 1 second. So now, when you're talking about frequency, you have to always mention that it is in 1 second, because if you don't mention in 1 second, you're not talking about frequency. You're not talking about frequency. Maybe you're talking about period, but when you're mentioning in 1 second, that's when you're talking about frequency. So frequency is the number of complete cycles that a particular wave can make. If you look at this now, I'm starting from here. If I'm starting from here, this is going to be my starting point. Going away from it, coming down, and going back up back to it. That is making an upward movement from a starting point, making a downward movement from a starting point, and getting to the starting point again. That is a single cycle. So now when you're not counting, you're trying to measure a wave's frequency, you try to check how fast the wave went up and down within 1 second. How fast the wave was able to go up and down within 1 second. So this is like 1, 2. So that wave now, the moments that it went up and down, the times it went up and down, completing one cycle at each point. That's moving like this, 1, like this, 2, like this, 3. So the amount of that kind of movement it can make in 1 second is what is known as the frequency. So it is measured in hertz, Hz. So frequency, it is measured in hertz. In some textbook, you see it as F, while in some textbook, you see it like a funny V, something like this. Something like a funny V. So in some textbook, you see like F, while in some textbook, you see it as a funny V. So depending on the textbook you're using, just be aware of it. So the next one we're talking about is period. period. So period now is talking about you don't need to, you're not trying to measure within 1 second. You're trying to check the time it takes it for it to complete just one cycle. The time it takes for it to complete one cycle is what they call the period. So as I said, they say the time it takes to complete, the time it takes for a complete wave cycle to pass a given point is called the period. So meaning the time it takes the wave to complete one cycle, whether it is up to 1 second or is more than 1 second, but just measure from when it starts from a starting point, going away and coming back and going back to starting point. That is taking an upward movement, coming to starting point, taking a downward movement, coming back to starting point. The time it takes to make this complete cycle is called the what they call it, the period. It's called the period. So that's for that. So now speed now, the rate at which the wave propagates through a medium. So the rate at which the wave moves from one point to another point in a medium. So that's what speed is. So now we've talked about these characteristics. Let's move on to the formula, or what's known as the wave equation. So this wave equation is a popular equation that everyone should memorize. Like, so long as you are going to be, if you are studying physics or you're going to write an exam on physics, or you're doing other engineering courses or courses that will be needing, you definitely need to memorize this formula because you will not get tired of it. As you move forward, you will see more use cases for this formula. So the formula is V equals F lambda. That's F, this thing is called lambda. V equals F lambda, where V is representing velocity. V is representing velocity. F is representing frequency, and Q and lambda is representing wavelength. So V is equal to F lambda. That's the formula for the wave equation. That's the formula for wave equation. V is equals F lambda. So let's see an example under this. So these are examples come up in this question, under this topic, under this the use of wave equation. So they would ask you to either find the wave speed, which is the same thing as the velocity, the wave speed or the speed. They might ask you to find the frequency of a particular wave, or they might ask you to find the wavelength of a particular wave. So it's just for you to know this formula. So depending on the question. So now once you are given it, they will ask you something like this. A wave has a frequency of 20 hertz and a wavelength of 5 meters. So wavelengths are always measured in meter. In some cases, you might see it in centimeter, but change it to meter. If you see it in centimeter, change it to meter. Normal SI unit standard. So then, what is the wave speed? So they're asking you for V. So you just plug in V equal to F lambda. So this formula can be twisted depending on what they're asking you to look for. If they're asking you to look for F, the formula will become F equals V over lambda. If they're asking you to look for lambda, lambda is going to be equal to V over F. So just it's the same formula, just it can be twisted in whatsoever way. But note what these parameters are. This one, V in this case is representing speed. F in this case is representing frequency. Lambda is representing wavelength. So in the time when you see the formula where they will put F, you know that F is representing frequency. But in case you see something like that's looking like a funny V, like this, something like a funny V, that case, that is going to be the frequency. And on this side, when they use that one, they will use, instead of V, they will use C. They would use C, where C is going to be representing speed of light. So usually when you're talking about optics, they will use that formula. So it's now be C equals that funny V representing the same frequency times lambda. So just down is just for knowledge sake. Probably when you get to see it, I'm just calling it out so you know, because in some questions you might think that thing is V and they're writing the equation or the equation wrongly. But when you see C in the formula, just know that they're trying to replace V with C. And when you see a funny looking V, just know that they're trying to use it to replace F representing frequency. So I hope we are good to go so far. Hope you are following so far.
Sir, please wait. Sir, wait. You said that the V is going to stand for the wavelength. And the funny V is going to stand for the frequency.
Yeah, yeah, the funny V stands for the frequency.
The other V stands for the wavelength.
No, the other V stands for the speed or velocity.
The C,
In this
the C stands for the wave speed
speed of
shape.
light. Yeah, C is still the same thing as speed, but now it's not just any speed. When you see C, you're talking about specifically speed of light, because speed of light is written as letter C. Is it clear?
Okay, sir.
Okay, so we can move on. So we can move on. Can you guys still hear me?
Yes, sir, we can.
Yes, sir.
Can you guys still hear me? Okay,
Yes,
so
we can
let's
hear
move
you.
on. So now, properties of wave. Properties of waves. So the first time we talked about wave characteristics, so you don't get to misinterpret them. So these are wave characteristics. So now we have properties of wave. That's the things that all waves they have, all waves they possess, or they how waves behave, something like that. So waves, they always undergo reflection. Waves always undergo reflection. So reflection refers to when a wave bounces off from a surface. When it bounces off from a surface, that's like all this kind of thing that you carry, probably use your torchlight, shine on a mirror, and you now face the mirror in one way. You will notice that the torchlight will reflect on the wall now, or your wristwatch, light is shining on it from the sun. Then before you know it is now reflecting a kind of lighted portion on the wall. That's because the light wave is exhibiting, is undergoing reflection. It's bouncing off the glass of your wristwatch, and getting deflected towards the wall. The same thing happens when you put a mirror. So that's particular characteristics where the wave is bouncing off from a particular surface, whether it's sound wave, light wave, whatsoever kind of wave. Once they are experiencing that kind of bounce off reaction, it's called reflection. So now refraction, on the other hand, is another property of wave where the wave does not actually bounce off. It does not actually bounce off. But in this case now, we're having the wave moving from one medium to another medium. Moving from one medium to another medium. So what I mean by medium is from one phase of matter to another phase of matter, either from air to liquid, or from liquid to solid, or from solid to just something like that. Something like that. That's what they call when waves are moving from one medium to another. So now refraction is when, as the wave is moving from one medium to another medium, the wave now maybe it is coming at a particular angle. As it hits that medium, it does not get reflected. It penetrates that medium. But now as it penetrates that medium, it now bends because of it has lost energy somehow. It then bends in a different angle because of as it's piercing through that region. It is probably going something like this. Let's assume this was a straight line, or this was a medium, maybe let's say it's a medium. Let me just call it a medium. Or water. We have the wave. Or let me use something horizontal. We have water, and light wave is coming from this like this. Then it strikes up the water and goes into the water. It will not just continuously go in that straight line. It will go like this. Then because of it changing medium from gaseous medium to liquid medium, it then bends. It then bends. That's coming like this, going like this. Then it enters the surface and it bends. So that bending of wave, because of how it is moving from one medium to another, is what is known as refraction. What is known as refraction. So this is the property of wave that usually tries to refer to when waves bend as a result of them moving from either from a dense medium to a less dense medium, or from a less dense medium to a dense medium, either from something like air to water, or from like water to air, from thick to light, or from light to thick. So that's what I mean by dense or less dense. So now the next property we'll be discussing now is the diffraction of wave. Diffraction of wave. So this is the spreading of wave when it encounters obstacles. So this one, I think one of the best ways you can see it is when all those ripples within water, when you are seeing water that is flowing or rain is falling and the water is making all those water waves. Then, or even when you just still water, you just tap it, causing a kind of spreading or water wave. It will be going in ripples. Then you now put something like a stick in front of that as the waves are coming towards a particular direction. You then put a stick. These waves, they will now seem to go around the stick. They will not just because of the stick is there, they will now hit and stop there. They would go around the stick. So this kind of movement where waves move around a particular obstacle or they spread around a particular obstacle is what is known as diffraction of waves. Diffraction of waves. Or when probably it's kind of happen when you're trying to shout, you are shouting from here inside the room, and your sound goes outside. Someone outside is hearing you. It does not just happen. As mean the room was completely tight and probably the wall was not able to penetrate. The wave will not go outside because they are enclosed. But if there's a small opening, the wave will find its way through that small opening and go out and spread out. So everybody that's outside, you cannot hear the noise. Though you might hear it faintly because the wave has lost energy. But so long as there's a part that the wave can pass through, the wave will pass through that part and be able to come outside the part. That's why you can, in a closed place, if there's a small hole inside, you can be able to listen from that small hole and you hear any noise that's coming out from that particular space. So that's characteristics of wave, to be able to pass through small obstacles and bend across those obstacles is called diffraction. So that's called diffraction. So now interference. So this is the interaction of two or more waves that overlap destructive and constructive, that overlap, first forming destructive and constructive interference. So this particular interference, now what's talking about, if you take let's assume you drop two stones inside water at two different points, drop them. If you notice, the two stones would generate kind of water wave, like ripple. Then as these waves are coming from their individual points, they will be spreading out. So when these two waves then they meet themselves, you will see something that is now formed like as if it is nets, a kind of net-like appearance on the surface of the water, a kind of net-like appearance. So this net-like appearance that is looking funny, something like this, like spider web, that stuff is what they call the interference. When the wave, they come to themselves and they then begin to form regions of something like this, something like circle, like space, like net, all those kind of net stuff. The spaces between nets, they form that kind of spacing as they move. So that's what they call interference. So this thing they call this interference. There are points where, as me, we had a net like this now, a net. I'm just trying to use a net to interpret it. We had a net. The points where the two threads meet are the point that they call the points of constructive interference in the case of wave. So the points where it's completely empty, the whole of the net, is called the points of destructive interference. So those points where none of the waves touched, those points are known as the points of destructive interference, meaning that anybody that is standing at that point might not hear, or if it was a sound wave, the wave might not reach the person because the wave will always be, for some reason, bouncing and passing the person, like spreading across the person. So that's what these properties of wave that makes wave behave like that is called interference, where waves, they interfere with themselves, and as they interfere with themselves, they then cause some areas where there will be wave intersection and places where there are wave voids. So this is what's called the constructive and destructive interference. I don't know if it's clear now. Does anybody have any question now? Can you guys hear me? Hello? Can you guys still
Hi.
hear me?
Yes, we can hear you.
Oh, okay. So that's for this one. So let's see what we have in our next slide. So next is the superposition
But
theory.
please don't be upset.
Okay, I'm
I think
listening.
like my network went out, so I think like again when we were like explaining that destructive and constructive interference.
Okay, destructive and constructive interference. So this is the kind of scenario where you see when you have two spots. Maybe you have, like, I use an example where you say you have two stones. You drop two stones on a still water. You just drop them, and as you drop them, they form their
So I
circles.
can't
Then as
hear
these circles
you.
are coming and they intersect with them like a net, they form that kind of net appearance on the surface of water. So that net-like appearance that they form is what is known as the constructive and destructive
I don't
interference.
understand what just happened.
Can you hear me?
I can hear you now,
Yes,
sir.
I can hear you.
Okay, so it's kind of net kind of appearance. So those points that are empty, let's use a net as I used initially. If you use a net, we have a net. The points where there is hole are the points of destructive interference. Where there is hole, there are points of destructive interference. Then the points where the two threads of the net intersect, those points are called the points of constructive interference. So those points, if it were to be sound wave forming that kind of stuff, those points will be the points you'll be hearing the sound the loudest. Then those points that are these holes, if you are standing at that point, if you're in a room and things from that kind of stuff, you would not hear any sound. Theoretically, that's what they said. So, but in real life, I don't think that kind of thing really happens, like, obviously, for different reasons. You'll not be able to notice because they'll be bounced off and so on and so on. But if you have an open space, maybe you might be able to observe something like that. But in real sense, I don't think it's in a room, you will not be able to experience it, because even if the thing has created the constructive and destructive interference, as the waves come and bounce off a wall, you know how, as they're bouncing, they would find a way to reach, clear off, or intersect with all those empty portions of the net. So that's just by the way. So that's what constructive and destructive interference mean. So now moving on to the next one, superposition principle. So this principle is kind of an extension trying to explain the interference property of waves. So the principle says that the superposition principle says that when two or more waves meet, total displacement is the sum of the individual displacements. So I think this one is something that you should just memorize or write at the one corner of your book while you are revising. That the superposition principle states that when two or more waves meet, the resultant displacement is the sum of the individual displacements. That is, the final displacement is going to be equal to the sum of the two individual displacements, the sum of the displacement of the two of them. So now, and I tried explaining what constructive interference mean and what destructive interference also mean individually. So I said when two waves meet in phase and their amplitude adds up, it forms is what they call the constructive interference. But when the two waves meet and the amplitude cancels out, is what they call the destructive interference. So in diagrammatic form is what I was trying to explain to you, that
Excuse me,
that
sir.
net explanation was what I was.
Please, I can't
Yeah, I'm listening.
slide. It's like the light. Yeah, I can't really read
Can you
what
see it
it
now?
is. No,
It's not
I'm
clear.
not seeing it. Not clear. Okay, it's okay now.
Is it clear? Okay, sorry about that. I
Yes, it's
think
clear now. Thank you.
so. This is the superposition principle. So this is what the principle states. So this, on the other hand, is the constructive interference definition. The simple definition, I said it's the understandable definition from physics. So, but if you try it's given to you as an example in theory, you would need to use the explanation I explained for you. At the points where these two waves, as they intersect, as they interact with themselves, the points where they intersect together, forming a cross or something like that, those points are called the points of constructive interference. And the points that are void of interactions are the points of destructive interference. So that's for that. So now this is an example, just a sentence example, sure. So two waves of the same frequency and amplitude, but one is inverted. The resultant is 0, and displacement is called destructive interference. So destructive interference, as I've said from here, I said it occurs when the waves they cancel out themselves.
I
When
still
they
can't
cancel out
see
themselves, that's
the screen. Oh, still do it again. I can't read
sorry.
the
I'm trying
write-up.
to keep full screen at the same time. I don't know. I tried sending this slide to the group. I don't know if you were there when I sent, so probably it might help. I don't know. Or just maybe you could, as you're on the call, just open the slide. And while I'm explaining now, I think if you are looking at this slide, you should be able to follow what I'm saying. Though only maybe the description, the annotation that I'm trying to show on the screen, you might not see it. But that's I don't know. I don't know what to do about that now. So that's for constructive and destructive interferences. So let's go on to the next slide. So interference patterns. So the interference now we have a kind of interference that is known as Young's double slit experiment that is used to tell interference pattern. So this experiment tries to demonstrate the wave nature of light and the formation of interference pattern. So in the experiment, they try to use something like an alternating light and a black band on a screen, and try to use it to create both the constructive and destructive interference. Or in this case for light, because mostly you would easily observe constructive and destructive interference in cases of sound. For the case of light, the experiment that is used to show that light too also undergoes constructive and destructive interference is this Young's double split or double slit experiment. So this experiment, you would use materials that are looking like what they call it, a single material. Then they will divide lines between it, and they will shoot a beam of light on one angle. And when you shoot a beam of light across that angle, the waves will then come out from the slits. And when this wave comes out, you will notice that point, as we had a square, or something like a square. Then on this square, let's use this white portion as a square. And we then had splits, one straight line, one straight blade cut that is open, like we could make a cut on one side, make another cut on this side. That is, we make one cut on this side, make another cut on this side. Then we shine light from the back of my screen. You notice that the light will come out through this place and light will show outside. But the place that if someone should stand in between this wall, the light would not touch the person because how the waves will move. Some portions of the outside of this outside wall would get light, but there's a point that within that place that will not get that light expression at all. So this is how to tell that this is like an experiment that's trying to point how this interference can be depicted, or in case of light. So there's a formula that can be used to that was gotten for the what they call it for the double split experiment, and that formula is used to calculate the interference or the distance between two points when you're trying to have waves. Waves at 2 points, because to create interference, you need to have two waves at two different points. Then their waves will then come and intersect with themselves, like what I said about the two stones at different points. So the formula that can be used to calculate either the distance between the waves is this formula given as sine theta minus m lambda. Sine theta minus m lambda. I don't know if you guys can still hear me.
We can hear you, sir.
Okay. So that's the formula that they can use to calculate the distance between 2 points of wave or waves at two different points. So now we have an example here. We have an example here where I tried calculating the distance. So we said light of wavelength 600 nanometer passes through two slits separated by 1 millimeter. Calculate the distance between the first order maxima and the second order maxima. So now this is, I don't think I've seen questions like this, but this question is actually from the experiment of from the double slit experiment. So this, to solve it, you just need to use this, the formula sine theta equals m times lambda. Can you guys even still hear me?
Yes, sir, we can hear you. I can hear you.
Just now that we start hearing you.
Okay. Okay, so this formula, the theta is representing the angle between the central maximum. So while lambda is usually your wavelength, so m is representing the order of the diffraction pattern. So this theta now here we are seeing is representing the the angle between the central maximum and the observed diffraction maxima. So these ones are just kind of like story. When you see the question, you would know what the theta is given as. So most times they can ask you to look for, might ask you to look for the theta. So the formula is actually d sine theta. Sorry, d sine theta equals m lambda. So where d, you can see it in some textbook as d sine theta n instead of m. They'll put as n. So in that case, you just know that your d is representing distance, theta is representing the angle, then your m is representing the order. I don't know if you guys are even following me at all.
So we did not get what
Hello?
you said. Your voice, we're not hearing you. We can hear you now.
Okay, so I was saying that d is representing the distance between the two, in this experiment now, d is representing the distance between the two slits. Then theta is representing the angle, while m, or in some cases you see it as n, is representing the order of the diffraction pattern. So usually they would state the order in the question most of the times. They will state the order of the diffraction most of the times in the question, or they might ask you to look for the order, then they'll give you other parameters. So lambda is representing the wavelength. So d is the distance or the spacing between the two materials that are the two holes that is experiencing the light diffraction. Theta is the angle, or you can call it the angle of constructive interference. So then m is representing the order, then theta lambda is representing the wavelength. So to solve this now, we are given the wavelength. So you first off convert the wavelength to meter, convert the distance to meter, then you can then solve with the formula to get your d. So this one, you're looking for the d. You're looking for the d. So in cases where you're not given the theta can be seen as 90 degrees. In cases where you're not given the theta can be seen as 90 degrees. So let's move on. So next we are going into sound waves. And properties of wave, talk about characteristics of waves. So now we are going into a particular type of wave now, and that wave is sound wave. We have optic waves we have sound wave, but we're focusing on sound wave. So now sound waves is a kind of mechanical wave. So when we are at the beginning, I said there are different types of wave. We have mechanical wave, we have electromagnetic wave. So mechanical waves are those ones that they require a medium to get propagated, while electromagnetic waves, they don't require a medium to get propagated. So now sound wave, we are getting to know now that it is a mechanical wave that that propagates through a medium due to the vibration of particles. So it's caused by the vibration of particles. That's how sound waves are being produced. When particles vibrate, sound is being produced. So if these particles are closer to themselves and they find it easy, when they are closer to themselves, they can easily vibrate. But when they are far from themselves, they would find it difficult. They will not be able to hit themselves to vibrate, or will not be able to notice the impact of vibration very well. So when we have, maybe we have, let's say we have bottles, like all these kind of Coke bottles, we place them together, or breakable bottle, we put them together, like we have them inside a crate. Then we are shaking them when it is full. When the crate is filled with bottles, we are shaking them. You notice that the noise you'll be hearing, the clattering noise, will be louder than when you just have two and try to shake it. You not really hear noise, but you'll be hearing noise, but you don't hear noise that much. So this is the idea that is behind the fact that solids make more noise than liquids and gases, because the particles of solid, they are closer to themselves. So when they shake, they can hit themselves, and because they can hit themselves, they will make louder noises. So sound wave transmits best in solids, next in liquid, then sparingly through air. I don't think I wrote this here, but just write this one down. Waves travels best or fastest in solids. Then next, then worst, that the worst points that they travel, or that they have the ability to travel, is in air, because they need medium. Sound waves, they need medium very well.
Sir, please repeat what you said. Sorry, you said waves travel best in
Solid, followed by liquid, then gases.
Thank you.
So from what I have here, I said it requires a medium to travel and cannot propagate through a vacuum. So sound, if you don't have either air or liquid or solid, you cannot hear sound. You cannot hear any sound at all. You cannot hear any sound. So if for any reason in space, if you carry two metal plates and be smashing them with themselves, if you go outside in the space, if you smash them, you would not hear any sound, because the sound waves will not be able to travel through that vacuum, because outside the space, there is no air, there is no solid in the atmosphere, there is in the environment, there is no solid, and there is no liquid.
Yeah. Please try if you can help me brighten this screen, please. It's affecting my eyes.
Sorry about that. Let me see. Is it brighter now?
Yeah, it's better now.
Okay, sorry about that. I don't know. Okay. So we have sound waves. Sound, and we said they require mediums to travel. If there is no air, that's in a vacuum, you would not sound, you cannot hear any sound. No matter how loud you try to hit two things, you would not hear any noise, because they need materials to travel. And it's in vacuum, there is no air, there is no liquid, and there is no what they call it, solid. So now the speed of sound depends on the medium and the temperature. So these are two factors that determine how fast sound will travel. So temperature and the medium, how compacted the medium is, which was what I was trying to explain. Solids, liquids, gases. Solids are more compacted, so sound will travel best through them, because once it hits one, it will be able to touch the next one and touch the next one, and it will easily travel. But when it is in liquid, it touches the first one, then before it will stretch, you stretch the next one. The other one, they are liquid particles, they are not that close with themselves, or they're not really rigid or organized that sound will easily move. So the liquids will kind of distort the sound, the wave movements or the sound wave movement. So for that reason, they travel best in solids. Then liquid is the one that is following next. That's the reason why when you hit two plates together, I don't even know the best example that I could give, but just get the idea that when you have sound, or you're trying to hit solids together, when you have solids, sound travels best in solid. Because I've not been in that kind of environment that is surrounded by solid, where I'll be just the material inside the solid. So, but by theory, sound travels best in solid, then next in liquid, then next in air. So now there are three properties rather of sound waves that I'll be mentioning here. Properties of sound wave. So we have pitch, loudness, and timbre. Pitch, loudness, and timbre. So for pitch, it's a property that is related to the frequency of sound wave. So it's similar to sound, but it's not to loudness, but it's not really loudness. It's different from loudness, but it's dependent on the frequency. You know, when someone is shouting on top of their voice, they say the person is being loud. But the person does not need to be using high pitch. The person is just shouting. You can hear a man shouting, and their voice will be deep. They are shouting loudly, but their pitch is not as high as when you see they have high pitch in their voice. So that thin, sharp sound that you hear when children scream, if adults scream, you will not hear that kind of sound inside, because adults don't really have large that kind of high pitch in their voice most of the time as they grow. But pitch is that sharp sound, that height that is dependent on frequencies of the particular sound wave. So amplitude, loudness on the other hand, is dependent on amplitude. Loudness is dependent on amplitude. So it is the louder the
Sir, please, you said
yeah, I
that
can
the
hear you.
pitch is dependent on what?
On
Pitch
frequency.
is dependent on what?
Frequency. Pitch is dependent on frequency. So then loudness is dependent on amplitude. Pitch is dependent on frequency. Loudness is dependent on amplitude. So then we have another one that is the third property that I listed here, and it's called the timbre. So this particular one is the quality or color of sound, which allows us to distinguish between different sources. So this is I know when you hear color, you wonder whether you can see sound waves, but in the sense, it's just talking about how you can be able to distinguish between different sounds. Is that property of sound that can help you distinguish, okay, this sound is coming from a string instrument, this sound is coming from a percussion instrument, this sound is coming from maybe a piano, a violin, or a drum. That's thing that gives extra beauty to sounds, that can help you to distinguish different sounds. You know, a human voice sound, you know, an animal voice sound. That quality of sound that can help you distinguish them is what they call the timbre. So moving on, we have another stuff that's called Doppler effect. This is another subtopic that's under this topic of sound, Doppler effect. I don't know how many of us have probably been moving on the road, and maybe a bike man is riding his bike and is playing music on his bike. Maybe let me think of a music. I don't know. I never remember any music clearly, Sha. But say a music, they are playing a music, then the bike man move past you very fast, and before you know it, you get maybe they're singing the song like I'm thinking of one popular song. I wonder why it is writing from my mind. So maybe something like someone should help me with a song, I beg. Someone in the audience should help me with a song. Just a song. So that's the thing I'm trying to explain. Is you have some the music is playing. You said?
Can I sing?
Yeah. You said?
I said, can I sing?
I'm not really hearing your environment. I don't really hear you.
No problem. There are noisemakers here.
Oh, okay, okay. So it's just that kind of thing that you hear. Maybe you're singing something like they are singing a song. I don't know why my head is blank. The song. So they are singing a song. Then as this bike is moving, you see like I said, the song is changing tone as things is going. The same song, but it's nothing like I say, something like that. The sound is changing. That kind of bend in the sound is what is known as Doppler effect. Doppler effect. So this effect is the change in frequency or wavelength of wave in relation to an observer moving, comparing it to a static source. So it's that kind of thing that you see that in your own music, in your car, you'll be playing the music, you are still hearing the music throughout the same way because you are moving with the music. But someone that's on the road will probably hear them singing, why am I not remembering any song? Don't worry, Sha. I don't know why my mind is blank on songs. But you're singing a song, then all of a sudden, it's like I say the song
Hello,
is
sir.
changing.
The definition again, please.
Yeah.
Define it again. I
Okay.
said the definition of Doppler's effect.
Yeah. See it here. It is Doppler effect is the change in frequency or wavelength of a wave. It is the change in frequency or wavelength of a wave in relation to an observer moving relative to the source. Moving relative to the source. So you can either see it when the source is standing, as you're moving far away from the song. You notice that the song, if you're moving on the song, when you came close to the sound of the place where they're playing the music, it's loud, but you start going far away, the sound starts changing. The pitch starts reducing, the amplitude, the frequency of the sound starts reducing. So that is Doppler effect. Or maybe you are standing at a place, then a car or a bike, usually I experience this very well in bike, when the bike is moving very fast, passing aside you. When the bike is there, you hear the song singing loud and singing clean, like the way you hear it. But as things is going, you notice that the thing is bending, the song is bending in a particular way. So this kind of effect is what they call the Doppler effect. So people that
Okay,
are in the case of
the source. Is it a stationary source or a moving source? From the definition you just gave us
it
now.
could be it could be a stationary source or a moving source. So it could be two types of source. Either the
But
source
when we
is
are
coming
defining it, we
towards
just say
you.
in relay, moving
Yes,
in relation to the source, just like
relative. Yes, yes, to the source of the wave. So now the motion can be static, but the wave, the source is moving, or you are moving and the source is static. So either ways, you will be able to observe Doppler effect so long as one of the two is experiencing motion. Either the source is moving or the observer is moving. So you don't experience Doppler effect. So Doppler effect is just that simple change in frequency or wavelength when this kind of thing happens. So now, example, a car moving towards a stationary object or a stationary observer with a horn emitting 400 hertz sound. As the car approaches, the observer hears a higher frequency. Once the car moves away, the frequency drops. So that's just the idea I was trying to tell you. So now when you see maybe a trailer that is pressing its horn from far, it's not been, you probably think press its horn, your mind will tell you it's not near you. But when it gets close to you and it presses the horn, it will be very loud. That loudness tells that it's already close to you. You're hearing a higher frequency of that same noise. It's not that the person now use more force to press his horn. The same way he pressed his horn at that instance, the first point, the same way he's pressing his horn at the point when he gets close to you. So it's just that you heard the horn at a different frequency. First it was at a lower frequency, but as it came closer to you, it became a higher frequency. Then if he goes forward in front of you, goes further, and he press the same horn, you will hear it low again. So that's what you're experiencing. It's not really that, it's not just distance that is happening, it's the frequency that is, you are hearing a different frequency of noise. The noise frequency is becoming different. So that's just the idea. And that this experience that you experience is called the Doppler effect. That's what's known as the Doppler effect. So now there's a formula for Doppler effect, and that formula is given as F prime equals F, that is F bracket open V plus V naught all over V minus Vs. So these are what all these things mean. V, ordinary V, is the speed of the medium, that is normal speed of the medium. If it is in air always has a constant speed that sound travels through it. Solid have a constant speed that sound travels through it. Water has a constant speed that sound travels through it. So that is what is representing the ordinary V, the speed of sound through air, the speed of sound through water, the speed of sound through what they call it, solid, or yeah, through solid. So these are the what they call it, the value. I think want to give you the value for your V. So then your VO is telling you the speed of the observer. So it can be 0 if the observer is standing. Then the speed of the source, it can be 0 if it's the source that is standing. So this is the formula. F prime. So the new frequency that you're hearing a different frequency as the speed changes or as the medium changes. So the frequency will be changing. So this is the formula to be able to calculate the Doppler effect. So now we have an example. We say a car moving at 3 meters per second. That's the speed of this. Let's see what is emits a sound. That means the car is one that's emitting the sound. So that means the source is moving at the Vs is moving at 30 meters per second. And it has a frequency of 1000 hertz. So our F is the frequency of sound that's been emitted. So that is 1000 F. So now the observer is stationary. That is the speed of the observer now is 0. Calculate the observed frequency. So they're asking you to find the frequency of the observer. That is F prime. F prime is the frequency of the observer. F is the frequency of the sound from the source. So now when they're asking you to find this now, they are using the speed in air. So there's always a speed of sound in air, and that speed of sound in air is 330. If I'm correct, 330 is the speed of sound in air. So it's a constant. 330. So when you want to solve this, I would like you guys to solve it, sir. I would like you guys to solve it and give me the answer. You guys solve it. I have like,
The
I'll give you
first
like
F, the first F, I can't see the coefficient very well. The first F, what's the coefficient?
it's just F prime. There's no coefficient. That's F prime.
F what? F equals to that F equals to
F prime.
that
That is
first
F
F.
prime.
So F what? 1.
Okay, F prime is equal to F1, something like that, or F0 or F0 or F observer. It can be F observer equals to F source equals F observer. Sorry, F observer equals F source, bracket open, V plus V observer, bracket close, all over V minus V source. So now in this question, I would like people to use the speed of sound
Sir, please
in air to be.
reduce your screen a
Can you guys
little
hear
so
me?
that I
Sorry, your
can.
mic is kind of
Sir, please reduce your screen a little so that I can get the
okay.
question. Thank you.
Okay.
Can you hear me?
Sorry. So
Can
this is the question.
Thank you.
Yeah, I can hear you. This is the question I've
you hear me?
So let's use the V. Yeah, can you hear me? Someone is calling my name. I don't know. So in this case, we're using our speed of sound in air to be instead of, let's not use 331, let's use 345 or 345
You said
because
something was constant.
331,
Yeah, you said something was
yes,
constant. Is it the F?
the speed of sound in air. That is the what they call the speed of sound V. Ordinary V. Ordinary V is constant, and it is what they call it 349. We use 349. but at 0 degrees, the speed of sound is 331. But at normal room temperature or something like that, it's around 349. The speed of sound is around 349.
Say it again, please.
Okay. Speed of sound in air is 0 degrees. At 0 degrees is 331. Speed of sound in air at 0 degrees is 331. Speed of sound at, say, let me say 20 degrees Celsius is 343. Speed of sound at 20 degrees Celsius is 343. Then speed of sound outside at around, let me say 25 to 30 degrees Celsius is 349.
Sir,
So
please
that's
come
a
again. It says speed of. It's coming
speed
in.
of
The
sound,
V, its unit is, so the V, its unit is in Celsius.
meter per second, meter per second, meter per second. So I was saying
Okay.
speed of sound at 0 degree is 331. Speed of sound at 0 degree is 331. Speed of sound at 20 degrees is 343. Speed of sound at around 27 to 30 degrees is 349. So now I want people to use 349 as your formula, as your V for this question. That is the speed of sound for this question. So I need to hear the final answer. Let's hear the final answer. I think we have just a few minutes left. So I want you guys to solve this.
Sir, please, we should solve which question. Is it the first one, or the second one?
This one here, this one here.
Okay.
I can't see the question though.
Okay, see it here. I've zoomed it in. I don't know who has gotten the answer. Who has gotten an answer?
1,000.
So, sir, I think we should use 349, Shay.
349, yes, 349.
The V you gave to us, change the V you gave to us is the speed of the observer.
No, the 349 that I gave to you guys
Okay.
is the speed of
Okay, it's
sound
the
in
speed
air
of sound. Thank you.
in the medium, yes.
Okay.
I can't really hear you. Someone's mic is mumbling. I cannot really hear what you're saying. I don't know if someone is saying something now. I don't know. I'm not hearing you clear. Probably end your what they call it, or cut your call and come back to the call again, because I'm not really hearing you. If you're saying something, I'm just hearing someone's mic mumble, like it's making one kind of noise, but I cannot pick anything that the person is saying. Just in case someone is saying something. So who has gotten an answer?
I got 1,000.
1,000. So let's see. Let's see who else got 1,000.
So what is VS? VS, what is
VS
it?
is the speed of the source of sound.
Hello, you said VS is what?
Is speed of the source of sound. Speed of the source of sound.
Okay.
So someone said they got 1,000. I'm trying to see who else had another answer. Who else had another answer?
So please, what's
Hello?
the VO? Like, what's the speed of the observer? Is it zero?
From the question, does it seem like it's zero? If you see it as zero, then it's zero. But from the question, just check the question because that's the reason why I said to solve the question. So we just try. If your mind is telling it's zero, then probably it's zero.
Okay, sir. Thank you.
You're welcome. So who has gotten an answer? I don't know who has gotten an answer. One person has said she got 1,000. I don't know who else has gotten another answer. Okay, so let me start solving this now. So first off, we know we're
So
looking
I
for f
got
prime.
1090.
Yeah,
Oh, yeah.
1090.
I
Okay,
got
so
Yes,
let's see. Let's
point
see.
zero.
1094. 1094.
That's the same thing I
Okay,
got.
okay, okay.
1094.
So so simply
So
put, the correct answer is
I got
1094.
hello sir. Can you
Yeah, I
hear
can hear
me?
you.
I got
Yeah, I can hear you.
1.094.
1.09.
Hello? 4.
You said you got 1.09. Okay, it's actually 1094.
Okay,
But
okay.
let's see,
Sorry,
probably
I
we'll
didn't
see where you
multiply with I didn't multiply with
with 1,000.
1,000.
1,000.
Yes. Yes, let me multiply.
So that's the answer. The answer is 10. 394. So it's that simple. You just put in your value for your V to be 349, your value for your VO to be observer is stationary. So the observer is stationary. So meaning that the observer speed is 0. That means the observer is at rest, the speed is 0. So VO is 0. So V is 349, then VS is 30, because they said the source, the car that is moving, that is making the sound, is moving at a speed of 30 meters per second. So the VS is 30. So our F, which is the frequency, is 1000 hertz. So putting it in the formula and plugging everything, you will get your final answer to be 1049. I think 49.04 something something something. So that's for
One
that one.
0
I used
9
I
4
used
one
3
0
instead of
4.
2.
Yeah, 1094. You said you used three what?
Yeah, I didn't see the 0 at the back of 3. So I used 3 instead of 30.
Oh, okay. So that was where the error came in from, if you had an error there. So it's 30. So I believe it's straightforward. At least everybody knows how to use the formula. It should be straightforward. Just know, remember the formula. Remember, I said physics is just all about memorizing formulas. If you can
Sir, does
memorize
it mean
formulas
that in the question they will not give the speed of sound?
of sound,
They
yeah,
will not
sometimes they
give
might
it.
not give you the speed of sound.
All
Sometimes.
right.
So it's best you should either use 343, preferably use 343, because that's the speed at 40 degrees Celsius, 40 degrees and 20 degrees Celsius, sorry. So that's close to the room temperature. So 343. So most times they might tell you exactly the temperature or the temperature. So when they tell you the temperature, you need to know what it is. So 343 at what they call it, 20 degrees Celsius. 331 at what they call it, at
At 0
0 degrees
degree.
Celsius. Yeah. So, but there's actually a formula. There's a formula that they can use to get it with temperature. So that formula, for that formula, you need the speed. Like you can use to get the speed. So the formula is 313. 331. So I don't know. Have I been saying 313?
No, sir, you said
Hello.
331.
Okay. Better. So the formula is 331.3 plus 0.603. That is, the formula is speed of sound V is equal to 331.3 plus 0.606 times T. That is 0.606 T, where T is the temperature. So this one is the kind of formula you can use to find at whatever temperature they give to you. At whatever temperature. So this is the formula that I can use to get the speed of sound in case they don't give you and they just mention temperature. And they mention maybe at 100 degrees temperature or 100 degrees Celsius. So with this formula, you should be able to solve and get it. So the formula is V, that's the speed of sound, equals, that is in air. This formula is applicable only in air. V equals 331.3 plus 0.606 capital T, where T is representing temperature. So that's another way you could see. They could, instead of them just leaving the question blank, they could have told you a car is moving at a hot afternoon with a temperature of, they'll give you a temperature. Then you might be wondering, where am I using temperature? Where am I using temperature? The temperature will help you get your V. So if you probably use maybe your common V that you know, maybe 343 or 349, you might get your answer, but your answer might be becoming confusing because you might not be close to the final answer. So that's the formula that can help you get the exact speed of sound at any temperature. So moving on, we'll be treating pipes and strings. Pipes and strings. So pipes and strings are examples of systems that can produce standing waves. They are examples of systems that can produce standing waves. I don't know who knows what standing waves are. I don't know who knows what standing waves are. Hello?
Hello?
Hi.
Hello? Yeah.
Yes.
Oh,
Hi.
can, Yeah, I was asking. I
What's
said
your
I
question?
don't know who knows what standing waves are. What are standing
What?
waves? Who knows what standing waves are or stationary waves? What are they? What are standing waves or stationary waves?
Stationary waves are waves that cannot, waves that are at a particular place, waves that cannot move. That's my own understanding.
Thank you. So they are waves that stay. Yeah, you are correct. You are correct. They are waves that oscillate at a specific place. They don't move. They just stay at a particular point and they keep on exhibiting wave-like pattern, but they don't move. They just stay at a point and be replicating that, like just staying, bouncing up and down, bouncing. That is how they appear. They just seem like as if they are bouncing at a spot continuously at a continuous spot. So they are known as standing waves. So waves that don't move, that don't travel, they are known as standing waves. So they occur as two waves. They occur when two waves or of the same frequency and amplitude travel in opposite directions. So these kind of things, they occur when you have this. I think this one is important that you should know that standing waves, how are they produced? They are produced when two waves of the same frequency and amplitude that are moving in opposite direction interfere with each other. So this is how standing waves form. I think it's very, very important that you take note of that. So they are formed when two waves of same frequency, same amplitude, and in opposite direction, they travel towards themselves. Same frequency, same amplitude, in opposite direction. So these three things are important. Two waves of same frequency, same amplitude, and traveling in opposite direction. When they interfere with themselves, they form standing waves. So they form standing waves. So,
When they do
Sir,
what, sir?
please, can you repeat?
okay, I said standing waves are waves that are they are formed.
Raise
How
your
they form
voice a
standing waves?
little bit.
Okay, can you hear me clearer now? Can you hear me clearer now?
I can hear you perfectly well, sir.
Okay, so as I was saying, standing waves, they are formed when you have two waves of the same amplitude, the same frequency, and traveling in opposite direction. When they interfere, you produce standing waves. So standing waves are produced when two waves of same frequency, same amplitude, traveling in opposite direction interfere with one another. You form a standing wave. So you form a standing waves. It's a standing wave, sorry. So what brought us into that is because of we're trying to talk about pipes and strings. So they are examples of systems that produce standing wave pipes, pipe system like fluid and stuff like that. They produce standing waves. So they can be open at one end or closed. They can be open at both ends, or they can be closed at both ends, or even open at one end and closed on the other end. So when these kind of things happen, the standing waves are formed, and these standing waves will then have a kind of altered wavelength when you have different types of structure of the system, whether open at one end, closed at both ends, or closed open at both ends. Like we know trumpets now, it's open at both ends. Trumpets are open at both ends, if I'm correct. Flute is an example. Flute is open at both ends. Flute is open at both ends. But something like mouth organ is open at one end and closed at the other end. It's an example of that kind of stuff. So then I think which one is closed at both ends? I cannot remember anyone that's closed at both ends, Sha. Okay, okay, no, maybe an acoustic guitar kind of, but it's not really. One end is open, but that's just the idea. You have some that are closed at one end, some that are open at one end, and so on. So now, in let me talk a little bit about the standing waves. Some of the characteristics of standing waves are this one is not here. So characteristics of standing waves is that they have nodes and antinodes. I think I wrote it here. They have nodes. Yeah, I think I talked about it. They have nodes and antinodes. I think so. Yeah, I talked about it here. Yes. They have nodes and antinodes. So I think you should just write it down. So characteristics of standing waves that they have nodes, N-O-D-E-S, and they have antinodes. 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 So nodes are points. I'm trying to define what nodes are. So nodes are points where the waves, the displacement of the wave is zero. Those points, like, remember when I was talking about wave at the beginning, I said you have a straight line. You have a straight line. Then you have, that is, your straight line is your balance, your equilibrium point. So then you are now moving like this. So those points, where the thing is coming to that equilibrium point, where the thing is getting to the straight line, where it's getting to the center line, those points where the waves are meeting at the center line, those points are the points that are known as the nodes. So standing wave is when you have one wave going like this, another wave coming in the other direction, another wave coming in the other direction. So that's how you produce
Sorry,
standing
sorry,
wave.
what is it?
Okay,
You
I
said that
said
nodes are what?
standing wave. Nodes are those points when the waves, or the two standing waves, or the two waves intersect at the equilibrium point. So when you have this now, you have a straight line now. You then move up, down, up. These are normal waves move. So the points where they meet their equilibrium center line, those points where they meet their center line is what is the node. So for standing wave is not just one wave. It's a combination of two waves. So we have one wave moving like this. Then we have another wave moving in the opposite direction to that same first wave. So that's how standing waves are produced. So we have something like this. Then we have another one moving like this. So meaning that when this one is going up, the other one is similar as if it's coming down. They are forming something like this, something like a circle, circle, circle. These are standing waves. They look like that. So that is how standing are formed. And that's those points when you have those circle, those points where those circles meet at the center is what they call the nodes. In case of standing wave, they are called the nodes. So then antinodes are points where the wave's displacement is at the maximum. That's this maximum height, either the peak or the crest. Sorry, the crest or the trough. That is the bottom or the top. So those points are known as the antinode. The highest point is known as the antinode.
So please come again. You said that
Come
there
again
are
now.
points where the wave displacement is at its
There are
sir.
points, nodes are points where the two standing waves, nodes are points where the two standing waves intersect. Like I said, there are points where the two waves in a standing wave system intersect. There are points where the two waves in a standing wave system intersect. So those points are known as nodes.
Then the
While
antinodes are what?
antinodes are the highest points of this node, or the maximum values of these nodes, the highest amplitude of these nodes, of these waves, I mean, is also known as the amplitude.
But sir, you said that that antinodes are the points where the two waves displacement is at its what?
Okay, from how I was saying it before, I think I said that there are places where where the wave displacement is at its maximum. So the place where the wave went its highest, that's where is the antinode. Same thing as the peak or the crest.
Thank you, sir.
Yeah. So now, examples of materials that undergo these standing waves, or that produce standing waves, are strings and pipes. So they produce standing waves. So that is examples of materials that produce standing waves. So for a pipe open at both ends, the fundamental frequency has node at ends and an antinode at the center. For a for a pipe that has two open ends, the fundamental frequency has node at the end and antinodes at the center. So while for pipes that are closed at one end, the fundamental frequency has node at the node. It has a node at the closed end and an empty node at the open end. So in the first case, you have node at one end, at the end, antinode at the center. So in the second case, we have node at the closed end. Then we have antinode at the open end. So meaning we have something like a pipe. Let's assume this our square now is a pipe. In a closed end, in an open end, let's assume this one is an open end, this open end. So what they're trying to say is that the node of the wavelength would have what they call it. They say it has node at its end. So that is at this point, you would have points where the two waves intersect. They would intersect at this point at the end here. The two waves will intersect at this point here at the end. So then the center point is where the antinode will happen. This center here, you would have the wave going like this, something like this. So that's how that one happens. So for the one that has closed, one end is closed, one of the pipe end is closed. They say it has node at the close end, meaning that this node, it will have something like this at the close end, where the two waves intersect would be on this end here. They would be like this on this end here. Then the place where it go like this, something like this, something like this, and it bounce like this and it will disperse at these two ends. Hey, they will disperse at these two ends. They would have their highest point at these two ends. So something like this, as if these are the wave will be something like this. And another one like this. So the two they will meet together at this point. Something like this, it looks something like this. Open end. Then at this end it will be closed. So it's just like as if you're trying to draw something like this, like a fish. Yes, I think that is the best explanation. Something like a fish. Fish-like shape. Fish-like shape. Here, going to this end, this top coming down to this end here. So that's how this one looks like. But for the other one, it's looking like something like an egg. Or not really an egg shell, but something like this. So that's for open at both ends, pipes open at both ends, and pipe open at be closed at one end. So there are formulas that they use to solve these things. So the formula, I think I'll be mentioning the formula later on. I don't know. Let me see how far we have. Okay. Let's see. So now the formula can be given as this. F, the fundamental frequency, the formula for the fundamental frequency is F being equal to V over 2L, where L is representing the length of the pipe. L is representing the length of the pipe. So this is the formula to get the fundamental frequency of the wave. So F equals to V over 2L for pipes. F equals to V over 2L, where L is representing the length of the pipe, and V is representing the speed of sound in air. V is representing the speed of sound in air. So it's just simple as that. They can ask you to find the fundamental frequency, and they'll give you your V, they'll give you your L, like how we have in this example. So you just plug and play, and you get that. You get the formula. So now, for strings now, the formula is different. So the formula is something like this now. But when we get there, we'll explain what it is. So for strings at both ends, the fundamental frequency has nodes at the end and antinodes at the center. So this one is looking like the pipe open at both ends. So it will have something like this. If the strings were fixed at both ends, as we have something like a guitar string, where we have strings like this. Then you tie it, you hold the string here, The string, the nodes will be at the end here. Like this kind of thing, it will be like this here. So that is the standing waves movements would be like. So we would have nodes at both ends, then the antinode at the center. So That is for that. So the formula for the fundamental frequency for string is given as F equals 1. Can you guys hear me?
Yes, I
Can you
can
guys
hear.
still hear me? Okay, F is equals to 1 all over for string. F is equal to 1 all over 2L, 1 over 2L times square root of T over U times square root of T over U is actually the, what they call it, the mu. T represents mu, and that mu is a constant that is for the string. So T is representing the tension. Then mu is a string constant. I don't know if you guys are following me. Hello?
Hello, sir.
Yeah?
We can hear
So I
you.
think, okay. So that's the formula for the fundamental frequency in string. So the former formula I gave you is the formula for pipe. So the mu represents the what they call it. Some people say is the what they call it is the mass density of the string. The mass density of the string. So that is sometimes it's usually a constant, or some places use it as the linear density or linear mass density. So it's usually measured in kilogram per meter. It's usually measured in kilogram per meter. So that's for this one. So now we have what is called harmonics now. Harmonics in pipes and string. I think that should be the second to the last. Yeah, that should be second to the last. Harmonics in pipes and strings. So harmonics are integer multiples of the fundamental frequency. So remember we were talking about in the previous ones, the formulas we were giving you was F, and that F, I was saying that F is representing the fundamental frequencies. So these fundamental frequencies now, harmonics are integer multiples of fundamental frequency. That is integer. When we talk about integers, that is whole number multiples of the fundamental frequency. That is, you're using something like 1 or 2 or 3 or 5 or 6 or 11, or there's something that does not have decimal. They are called integers. Numbers that don't have decimals are called integers. So when you have an integer multiplying the fundamental frequency, it gives an harmonic. So that's what harmonics are. They are fundamental frequencies. They are integer multiples of the fundamental frequencies. So for pipe, they are given as for pipe open as both ends, the harmonics are given as integers of f1, f1f, 2f, 3f, and so on. And so on. So for a string at both ends, that is fixed at both ends, the harmonics are also integer multiples of the fundamental frequency. So the same thing applies when you multiply a constant or a whole number. Let me not call constant. When you multiply a whole number by the fundamental frequency, you will get an harmonic of that particular frequency. So that is the idea behind the harmonics. I think something like that comes out once in a while. They ask you what are harmonics or something like that. They'll probably tell you which of these describes what harmonics are, or they'll ask you the property of waves in pipes or stuff like that that is the multiple, or that is an integer multiple of frequency, is known as dash. They'll now give you some maybe timbre. They'll bring different things that are nonsense and they'll mention harmonics at the end. Then that's the answer is going to give you the harmonics. It's the harmonics that is the integer multiple of that. So now applications of sound wave. Sound waves are used in submarines. They are used in medicine, in ultrasound. They are used in music, as we know, and so many other use cases. So these are the basic. They're even used in seismology. Seismology, monitoring earthquake. Knowledge of sound waves used in monitoring earthquake ultrasound. So now that submarines, they use it to navigate. Sharks also use sound waves to move through water. So these are the applications of sound wave. And with all this, I will say we've gotten to the end of this week's night class. I don't know if anyone has any questions so far.
No questions,
I don't
sir.
know if